Okay, this is the information we've been given. We have two pot things. The surface area of the smaller one is that, the bigger one is that. They've told us the volume of the bigger one, and we have to work out the volume of the smaller one. So this is an area volume scaling problem. And this is the best way to do these sort of problems. Write it out the way I've done it here, with the area and the volume of both of your objects. And next we're going to introduce a third thing. I'm going to call it D for both of them. And D is just a linear dimension. It could be the diameter of the base, for example. Why not? Let's call it the diameter of the base. It doesn't really matter. The point is that it's just a one-dimensional quantity. So there's D and D. We call it diameter of the base. Now, we can work out the scaling factor of the areas, and that's where we'll start. So what number did we multiply 120 by to get 750? Well, 750 divided by 120 is 6.25. Okay? So from the information they gave us initially, we can straight away work out the area scaling factor. Okay? That's 6.25. Now, with area, volume and single dimension scaling problems, the area, volume and D all scale with different scaling factors. It's not as simple as just dividing that by 6.25 to get this volume. What we're going to do is go from the area scaling factor, we're going to work out the diameter scaling factor. And to do that, you quite simply take the square root of the area scaling factor. So in your calculator, do the square root of 6.25 and you get 2.5. Okay? So we know that the diameter scaling factor is 2.5. The reason you take the square root is because the linear dimensions, such as the diameter, if you know that scaling factor, the area always scales with the diameter scaling factor squared. And that's why we took the square root of 6.25 to go in the opposite direction. What I'm talking about is this. If you have a square, say, of side 2 by 2, then the D, the linear dimension, D is 2, okay? If we double that and make a square of 4 by 4, okay, so the scaling factor is 2, because one side, D, is 2, and here it's 4, so we've multiplied the D by 2. But look at the area. The area, well, the area of this one is 2 times 2, which is 4. The area of this one is 4 times 4, which is 16. You see, the area has not gone up by the same linear scaling factor. It's gone up 4 times, which, as I promised you, was the linear scaling factor squared. 2 squared is indeed 4. And if this was done in 3 dimensions, so we had, I'll do it again, so we had a 2 by 2 by 2 cube, okay, 2 by 2 by 2, the volume of that is 2 times 2 times 2, which is 8. When you increase that to a 4 by 4 by 4 box, okay, 4, 4 and 4, The volume of this is 4 times 4 times 4. 4 4 is 16 times 4 is 64. So again, the linear scale factor, D, is from 2 to 4, which is 2. But the volume scale factor, again, it's not 2. Area and volume get bigger faster than the length of one of the sides does. In the case of area, you square the linear scale factor. For volume, you cube it. So 2 cubed is 8. So that's the volume scale factor. 8 times 8 is indeed 64. And that's what we're doing here with this problem. We found the linear scale factor, it's 2.5. So we worked that out from the area by taking the square root. And now we're going to go from here to the volume scale factor. If the linear scale factor is 2.5, we know that the volume scale factor from all this is the linear scale factor cubed, which is 15.625. So that's the volume scale factor. So times, we're going to multiply by 15.625. So whatever the volume of the smaller one is, it's this divided by 15.625, because this volume is 15.62 times bigger than this volume. So to work out the final answer, just put 1600 divided by 15.625. Put that in your calculator and it comes out at 102.4 centimeters cubed, because it's volume. That's it. So final answer, 102.4 cm cubed. And that's how you should do area volume scaling problems. Notice we didn't need to work out anything here. That's just a tool to work out the linear scaling factor.